Hey, very good afternoon, students. Welcome back to the class of graph theory, and we were discussing a few of the concepts of tree under Unit One introduction. Hope I'm audible. And please, someone acknowledge whether my screen is visible too. Yeah, very good afternoon, students. Yes, great. Hmm. So, before going into the content, the topics, I just want to quickly highlight about the attendance. Only few classes were finished, around six classes, I guess. Out of these six classes, it's a initial time to comment. It's very early stage to comment, but however, it's my duty to just to give a heads up. I have found so many students like Teja is haven't attended any of the class till today, and Somit, he has just attended the first class and is absent. So, and Vishnu, it's also the same. Vishnu, Rahul, right? And yeah, these four students. Uh, I hope they have joined this time. Uh, Not sure. Not sure those students are present, but yeah. And the others who are um, mix of attending, not attending. Just a quick heads up. Make sure you attend the class for that, you know, to be eligible for the end exam. There is something called attendance policy of having some 75%, and if there is a shortage of attendance and there are different procedures to tackle. Hope let's not get into those. So going forward, uh, students, please attend the class regularly. CR, can you please quickly check on these four? Uh, Teja, that is 132, probably last year guy, I guess. And Somit, 54, Vishnu, and Rahul. So I want these four students to be present from at least, if not today, at least from next class. If there are any mm, issues from their side, please tell them to contact me. All right. And the others who are in like three or count out of six, just a caution, don't miss these classes. And others, they're doing great. Don't get carried away and miss classes. That's what I say. Regularly attend. Okay. I see some comments here. We'll see that later part. So, with respect to the syllabus, we almost covered this part. Trees will be covered, and probably in this class, if possible, also the whole first unit. I will try to push it. But yeah, maximum in this week we'll try to cover the unit one. Okay. And for all my notes I already uploaded. Still I am referring to uh, nothing dio graph theory. So just a heads up. Okay. And we yesterday, I'll resume yesterday's class. We got to know what are trees and some of the properties of trees. And we also touched base to what the concept of pendant vertex in a tree. So yesterday I did, you know, took some time to convey this, and probably I didn't convey appropriately. And so the overall point is we know what is pendant vertex for this the given example. Yes, the first one is also a tree with pendant vertex is 0 here because it doesn't have any edge. But for the rest, there are pendant vertex. And the second graph, there are two pendant vertex here two, and here three, right? So we claim that for any given tree, mm, there is always one or more pendant vertices, right? Only if the graph has more than two vertex. If the graph has more than two vertex, the reason why we claim this is one or more pendant vertices in a given tree, if the number of vertices are greater than or equal to two, the main reason is because it's a tree, means there is it's a connected graph. First of all, connected graph, it's a tree. There is a path between every pair of vertex. That's why the connected concept comes. And it's a minimally connected. When I say minimally connected, there are no circuits. So definitely n minus 1 edges. So considering this fact, and every edge will contribute to 2 degrees. That is the starting vertex, there is one contribution, and the ending vertex, another contribution. So 2 degree every edge will contribute. So number of edges are n minus 1. So all the edges n minus 1 will contribute 2 into n minus 1 degrees, right? 2 into n minus 1 degree, which is span across n vertices. And since no vertex can be of 0 degree, we must have at least two vertices of degree 1 in tree, and this is of course n is greater than 2. And we are just talking about where a tree has more than or equal to two vertex. In that sense, we can say that uh, every tree has one or more pendant vertices, right? So going to an application part of a pendant vertex. So we stopped exactly at this point in the last class. There's a problem here. So what the problem is, a sequence is been given, set of numbers, total 9 numbers, 9 different numbers. It's not an increasing or decreasing, it's random numbers. And in this sequence of numbers, need to identify or find a increasing subsequence. Okay, this is a quick problem here. So can anyone tell, like, what are the possible sequences, increasing sequence? If I ask for a possible sequence, there are many. I will reframe it. The largest increasing subsequence, right? A largest monotonically increasing subsequence. So in this, mm, let me switch to the chat window also. Like for example, if I want to give a solution, so after 4, I can't consider this 1 because it's not a increasing number compared to 4. But however, I can consider 13, 4 and 13. When I consider 4 and 13, I can't consider others because 13 is the maximum. So yeah, some students say 0 to 8, 11, 0 to 8, 11, perfect. So all understood. I mean, what is this problem is all about. We'll see the solution in detail, but I just want all the students to be on same page, whether they did really understand what this problem is, to finding a largest increasing subsequence. So yeah, definitely this is one of the answer for sure. But is this the only answer? Graph theory will probably tell us more on this. So how best we can, solve using graph theory, we'll see. So what I did is, I've taken one start vertex. It's just an extra vertex. and I have made a tree of all other 9 digits: 4, 1, 13, 7, 8, 2, 8, 11, 3. Right? So now from this, now considering the 4, I will make further increasing subsequences. For from 4, what all possible things are considered for increasing subsequence? 13, yes, 7, 8, and 11, because all these numbers comes after 4 and they are greater than 4, right? So in that sense, initially what we did, we took some start vertex, and we have all the sequence, the given sequence, we have made a connection and made it at level 1. This is if considered. Wait, I'm trying to represent all these numbers in a tree, basically. So even though the root is considered as a dummy one, but the root is level 0 and the level 1 are the actual numbers which um, the sequence represent. So from 4, now all possible increasing numbers which comes after 4 and they are increasing order. Right? Next, if I check for 1, we'll get all the numbers comes after 1 and they are increasing order. And for 13, there is no, because 13 is the highest. So no other number is appeared in that sequence greater than 13. And similarly, 7, 0, 2, 8, so on, right? So I got a level 2 information or level 2 tree, leaf nodes. So similarly, again for next level, if I try to do, I will get this, this is the whole complete tree. So next level is 8, 11 for 7 and 11 for 8 and so on. So like for every node, we start finding such pattern, and to generate, if we keep generating a tree, this is the overall tree structure, which tells start from here, and each path, right? Each path will tell increasing subsequence from that particular number. So say for example, from 4, what are the increasing subsequences are there? 4, 13 and 4, 7, 8, 11, 4, 7, 7 and 11, 4, 8, 11, 4, 11, right? So similarly for 1, 13, 7, 0, we can easily, pictorially, I can give all the subsequences. But the problem was to find the largest. So in this largest, if we see that the height of the tree is the largest. So in that sense, this is level 4. At level 4, what all the numbers we got is the maximum highest. So level 4 means this level. If I backtrack 4, 7, 8 and 11. So if I quickly check 4, 7, 8 and 11. Yes, this is one of the largest subsequence. And the next is 1, 7, 8 and 11. 1, 7, 8 and 11. And yes, there is one more. 1, 2, 8, 11. That is, I've given the solution. 1, 2, 8, 11. And then majority of the students did say about the 0 to 8, 11. 0 to 8, 11. So there are 4 answers to it, and each answer having a length of 4, right? Length of, let's see, such a tree used in representing data is referred as a data tree for computer programs. So, a quick question. Yes, this problem we've definitely found a, all possible answers and the utmost correct answer. When I say utmost correct answer, because above this there can't be any correct answer, and students also, a few students did answer yes, see, these are also correct answer, but uh, we got 4 set, right? 4 set, that's the highest level of correct answer. So from graph theory we could able to solve this so easily. It just gives us our our brain works as simple as possible when we try to draw a tree and to make it. But by just seeing at the sequence and we are trying to find the largest, yes, we could able to find one, two, but brain tumbles here and there. We can miss one of them, right? So graph theory and being a tree, this is one of the a simple application which I wanted to highlight as per part of pendant vertices which comes under tree. Now, quick question to students. So, uh, what is the time complexity to construct this tree, this the final tree? In terms of right now, it is 9 elements considering n elements. Exactly for this problem, I want some answers in this chat window. Time complexity to construct a tree and log n great. We go of log n. No, it's not n log n, it's log n. Huh? Okay, great. Fine. Then, any answers? I want all possible answers. I'm looking for all possible answers. Construct this. The question is to construct this tree. You can also mention the base if you are aware of base concept, like log to the base, 2, 3, right? So, any other answers? Mustafa, am I audible? I feel that somehow I'm not. Oh, suddenly some answer came. Yes, sir. Can you again ask question? The question is, right now we saw this application. So in such sequence is been given of length n. Right now it is 9, right? The sequence length is 9. So if any such sequence has been given of length, say n length in general, so what is the time complexity to generate this kind of graph? I am not looking for an optimum. Just now we made, right, from say from this level to this level and all possible finding out. So what is the time complexity? Definitely space. You can take a relaxation. You have enough space to do that. Now, yeah, I got a few answers like log n to the power of 4, n log n, big O of n, and question mark, few question marks. So that indicates there's elementary of doubt. Okay, and big O of n log n, big O of n, big O of n log n square, big O of n into n, that is n square. Okay. Yeah, this is what I was expected to get. I mean, I was expecting such answers, a wide variety of answers, and definitely it's not a log n. Maybe log n if we want to traverse from head to toe leaf node. So out of 9 elements, um, to reach the leaf, I need time of log n in general. But again, it is not based to the 2. It will be based to the any thoughts about base. If I'm using log here concept, what should be the base? Base? No such base. The overall point is it log to construct this tree doesn't take log n time for sure. Definitely not n log n. N log n. Because see, simple, very simple, it is n square. Okay, it's n square. How I consider this, if I'm looking for 4, considering the first element, I will traverse all the elements once, and then I place their respective under 4, right? And then when I move to for the first element, I checked all the n minus 1 elements. For the second element, again, I check for all the n minus whatever the elements. Again, for the third element, 13 has come. I have checked rest of the elements. So right now it is 9. Looks like has been nearing to end. It looks like only 1 or 2 checks, but when we consider for n, it is 1 element with rest of the n elements. Again, 1 element with rest of the n elements. So such checks will go happen for n times for all n elements. So that's why it's a bigger bound. Even though it is lesser than that, we are giving an upper bound for it. So big of n square it is. Somebody saying log n to the power of 4. No. We concept. No, I can't even think of this one. But yeah, we can't mention log n to the base 2, because every child can have, or any node can have multiple child. It's not that only 2, right? The search space which doesn't divide into 2, like in binary. When we make a binary trees, at a root node, we'll make a decision, or we either will take left or right. So when we take left, the right part is completely untouched. So we are excluding half of the tree. So that's why the concept, based on the number of child, the base concept will comes into picture. Right now, in this case, it can be base can be under 4 4 node. There are 4 element. That's the first level, first node. It has 4 child. In the second element at the first level, number 1, it has 6 child, right? So children, it's just a tree. It's not a binary tree to have a restriction of only this number of child. So just to connect with the existing knowledge, I asked this question. Okay, so we understand how base work, log to the power of base, but in our case it can be n. So tree can grow to high n level. What I meant n level. So imagine this sequence is already in ascending order, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So for 0, the length could be like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? So the height of the tree would have been 9 instead of 4. Right now it is 4. So usually the height of the tree will tell us how widely spread the tree is. Correct. Yeah. Any questions? Yeah, it's definitely not related to graph theory, but just wanted to connect the things which we understand right now and we already have a knowledge based on data structure. Tree was able to map few of the concept. Hopefully, it is pretty clear now. Correct. Yeah. Okay. Going to a concept called distance and a center under trees. So, given this figure, so intuitively we can say B is the center of this tree, because it need just an one link or one edge to reach to the all the pendant vertex, or probably all the farthest pendant vertex. The farthest pendant vertex is by distance 1, right here 1. So by looking at only we can get to know that it's almost in center, even though geographically it is not center. Okay, can be again debatable. Geographically it cannot be a center, but intuitively it is B is the center. So in trees, there are concepts called center, distance, and path, and couple of more probably we'll see in the next slides. First, we'll see what is the center, and then we'll define what is distance. So we just saw for this tree, B is the kind of a center. Uh, in a connected graph G, we always start with a connected graph G for a tree because it has to be connected. Minimally connected. Minimally connected is the right word for the tree. The distance d vi vj between any two vertexes vi vj is the length of the shortest path. That is the number of edges in the shortest path between them. So right now for you know a we'll see with a bit more higher level rather than a tree. Considering a graph, now I'm not pointing to just a tree or specific to tree, but at a graph level. This can be applicable to graph level also. So the definition of a distance between any two vertices is valid for any connected graph, not just tree. In a graph that is not a tree. In a graph that is not a tree means the graph is not minimally connected. It is heavily connected. Means it has circuits. As simple as that. It has self-loop, parallel edges, as well as circuit. There are generally several paths between a pair of vertices. That's why I call circuit. There are more than one path, but in a tree, there is exactly one path. We have to enumerate all these paths to find the length of the shortest one. There may be several shortest paths. So in this graph, if I consider V1 as one vertex and V2 as the other, so how many paths are there like to reach a V1 to through A? Let's name it through edges rather than vertex. A and E is one. A C F is one. B F is the other. B C E is the one more. B G I K B G H is the one more. So many paths we'll get. But which is the shortest one has the less number of edges. So in that case, AE and BF, A and E, then B and F are the shortest path. As we don't know the weight of the edge right now, it's just labeled as one edge. So we're considering it's a one hop. So from V1 to V2, there are two hops. That is using edge A, that is one hop. The other one is the other hop. If the weights are given, it's a totally different story in finding the shortest path. So hope the things are clear. So between V1 and V2, it's two. It's not V1 and V2. It's VI and it's V1 and V2 only. Yeah, it's V1 and V2, not VI VJ. V1 and V2 is length is 2. The shortest path having a length is 2. In a tree, since there is exactly one path between any two vertices, we saw this in a theorem. In the first theorem of under trees, the determination of distance is much easier because we won't get multiple paths, we'll get only one path. So from A to B is 1, A to D is 2, right? Then A to C is 2, C to B is 1, and so on. So we'll get for every pair of vertex, we'll get the exact distance, and it's easy to find there will be only one value between a pair of vertex, the length value or the distance value. There is only one distance value for every given pair of vertex, and that is the shortest one, as simple as that, between given pair of vertex. Right. So before calling it as a distance, first we'll call that as a function between x to y. So as if v1 to v2. So before we legitimately call a function of two variables a distance between them, we have certain requirements to satisfy. What are those? Non-negativity, symmetry, and triangle inequality. Non-negativity is, if I consider right now, just before claiming that it is a distance, we'll call that as a function f of x comma y. X is a vertex, y is also a vertex. So function x comma y is greater than 0 and f of xy is equal to 0 if and only if x equal to y. X equal to y means both the vertex are incident. It's one and the same. Means a single vertex in a tree. For example, we saw initially this one. This is also a tree where x and y are same. F of xy is equal to 0, right? There is no edge. That's what it means. It's always greater than 0. If it is 0 means x and y are the same. Because no, I mean, I don't need further explanation to justify on that. But if there is an edge, definitely it is more than 0. So every hop is considered as one count. That's what I mean. X is symmetry. F of xy equal to f of xy. So it should not change at all. The distance is consistent. Symmetry. It can be also f of xy equal to f of yx. Not in all the cases because it's a in a there is a concept of directed graph and these are all what we saw is undirected graph. There is no direction. It is, if I can go from V1 to V2 through AE, I can come back from V2 to V1 through the same thing. But as the graph concept increases, there are concept of directed and undirected. So right now we'll just stick to f of xy equal to f of xy. It's always the same. Triangle inequality. So triangle inequality is if any pair of vertices has been taken xy and its function, that distance calculation function is always less than if we introduce any intermediate vertex to that. That is the summation of distance from x to z and z to y for any z. Any z is an intermediate vertex. So this will be always less than or equal to. Right? So in case of tree, it is always equal. It should not be less because there is only one path. We know that if I want to reach from x to z, if I have to take y as z, and then I have to take y as z. That's how it is. So in tree, it is equal. In general, in graph like this, yes, it is less than. For example, if I want to go from V1 to V2, I can go from via this node also or probably this node also. So if I take A and E, it is 2. If I take B, G and H, it is 3. So I have introduced 2 here, not just Z, Z1 and Z2. So addition of X to Z1 and Z1 to Z2 and Z2 to Y. Such additions. It's not just one addition, it can be such additions from intermediate nodes. So now we saw the functions and their requirements to satisfy so that we can call a distance. So now considering the fact that a distance between two vertices of a connected graph satisfy condition 1 and 2 immediately and evidently. Yes, these two, whenever the connected graph is being given, these two automatically will be, these requirements will be satisfied. But however, the third one need to cross check it by, first of all, whether the intermediate vertex present or not, etc. and so on. If there is only one path, then it is equal. Otherwise, it will take less than. That's what the whole point here is. Okay. Now, there's a theorem. We'll quickly check on the theorem. We have a fair knowledge on centers as well as distance now. So we are good to comment on something related to center. Every tree has either one or two centers, not more than that, right? So I have a tree here. So to prove that, I have a tree here called T, and every vertex has a number. Can anyone tell what is that number? Uh, can anyone tell what is that number is? Probably I've already written it there. Okay. So basically, it's a distance from vertex V to Vi. So Vi is a pendant vertex. So from farthest distance, this. So from this particular pendant vertex, if I want to, I can go to say how many vertex are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There are 14 vertex, right? So starting from the first vertex, I can go to 13 vertex. So the distance will be as the number of hops. So the highest hop is considered in this label. So from here, if I reach to here through one hop and two hop, but to reach here again two hop, 1, 2, 3, 4. To reach here it is 4. 1, 2, and 3. To reach here it is 3. 1, 2, 3, 4, 5, and 6. To reach here it is 6, and to reach here it is again 6. To reach here less than 6. So that's how this pendant vertex got 6, farthest distance. So all vertex got their respective value. So from this vertex, that is C, the maximum I can again reach to 13 other vertex. The maximum distance is 1, 2, and 3. 1, 2, and 3. From here again 1, 2, and 3. 1, 2. This is 2. So this got a weightage 3. I mean the vertex labeled as 3. Okay. So the maximum distance, max distance between a vertex, we will check for all vertex to its pendant vertex, right? So all vertex to its pendant vertex. From a given vertex V to any other vertex Vi occurs only when Vi is a pendant vertex. Because pendant vertex usually will have the farthest, will be incident or located at the end side. With this observation, let us start with the tree T having more than two vertices. Yes, it's a tree having more than two vertices, and it has its respective distance measure also. Tree T must have two or more pendant vertex. Yeah, of course, it has more than two pendant vertex in this case. But the theorem which we are trying to solve is every tree has either one or two centers. So if I do an operation like delete all the pendant vertices from T, the resulting graph T dash is still a tree. So I have removed all the pendant vertices like this one, this, and this, as well as this. So the resultant graph is still a tree, right? It's a T dash. Now again I have mentioned the distance from every vertex to every other pendant vertex. So for this, it is 1, 2, 3, 4, and 1, 2. So 4 is the highest, the weightage got 4. Similarly to all. Right? So after deleting, the point is what about the eccentricities of the vertices, like non-center things, right? How those values will reflect, or how the values will change with respect to all nodes. So by removal of all the pendant vertex from T uniformly reduces the eccentricities of the remaining vertices by exactly 1. And yes, we saw that Earlier it was 5, now it has been become 4. Earlier it was 4 and it became 3, and 3 has become 2. Those vertices are present, definitely they have reduced by 1 by removing a pendant vertex. But few pendant vertex are no more there, and their weightage from 6 to become 0 because they are not there at all because we removed it. Right. So coming to the point, all the vertices at T at a centers will still remain the center at T dash. So considering this as a center, because it can reach to the every other pendant vertex with less distance. When I say less distance, if I consider this as a tree, it can reach to these pendant vertex to less distance, but to reach these pendant vertex, it takes more distance. But see, 1, 2, 3, at max 1, 2, 3, at max it is 1, 2, 3. So intuitively, this is the center for this tree. So after removing pendant vertices, still the center remains the same, right? So now, furthermore, removing again a pendant vertex. Students, am I audible first of all? We get some noise. I hope it's pure. Okay. Yeah. Fine. So now, further, after again removing pendant vertices from this T dash, we get a T double dash, and we can see that exactly the vertices which are not in center, or probably the eccentricities of all the vertices, are reduced by 1. Earlier it was 3, it became 2. The weightage 2 became 1, and the 3 became 2. And center remains the same. So if I do further, remove the pendant vertex, the only one vertex will be left out. So in this case, yes, one vertex is left out. So we understood that every tree definitely will have one center. Is it possible to have two centers? Yes. Is it possible to have three centers? No. In that case, three centers are there. Again, deleting will get only one center. There's no point of going three, but we'll see what is having two centers. Okay. So this is one of the quick example for the same theorem. Uh, right now, I have mentioned the farthest distance from one vertex to the all the vertices, farthest distance. Uh, to reach this pendant vertex, it is 3. To reach this is again 3. To reach this pendant vertex, it is just 2, and so on. So I've taken 3, 3. After removing the pendant vertex, it becomes 2. So when we keep removing the pendant vertex, either a vertex at the end, when I say recursively keep removing until we find either a vertex or an edge, right? In this case, we found an edge. If I remove the pendant vertex, the edge will vanish and there is no graph or no tree. So theorem says every tree. I'm not talking about a no tree here. Theorem claims that every tree. This is a tree. If I remove these pendant vertex, there is a no tree. So we are not talking about no tree things, right? So every tree has either The center here, this is the center, which is the distance from the center of the tree to the farthest vertex. Farthest vertex in a tree is defined as the radius. So we know what is center for a given tree, and from that center to the farthest vertex is called a radius. So yeah, that is fine. If a tree has a center or two centers, does it has a radius also? So for one center, yes, we got to know. For the two center thing, this is the example. What is the radius is the question. Yes, we have a radius concept. So considering this as a center, the farthest distance is 2, right? Farthest distance is 2, and for this the farthest distance is 2. So the radius is 2 here. It's not that this is the center, I will take this distance 1, and for this vertex this the distance is 1, so I will take 1. No, its farthest distance is 2, the radius is 2. Okay? For instance, the radius of this figure is 3. Okay, the above one we are talking about the radius is 3, and for the below one the radius is 2. I will see diameter concept. The diameter of a tree T, on the other hand, is defined as the length of the longest path in the tree. Note, a radius of a tree is not necessarily half of its diameter. So the diameter is for this the diameter is 6. The largest or the length of the longest path from this vertex to this vertex, the longest path, the length of the longest path is the diameter, right? So the center is 3, diameter is 6. So it's exactly half in this case, but however, the diameter is 3 here, but the radius is 2. So, right? That's why a radius of a tree is not necessarily half its diameter. One quick application, just a general. You already know the concept of tree. In this case, there are 14 nodes. Let's consider it's a sociological application, just to interpret. In a social platform, there are 14 people, bunch of people in a group, or probably in a society. They are connected, minimally connected via tree. So the point is, if any person wants to communicate to any of the person in the society, is possible directly or indirectly. When I say indirectly, through via other members or some other members, right? So the group cannot afford to lose any of the communication links. The edges are the communication links. The group cannot afford to lose any of the communication links. The eccentricity of the each vertex EV represents how close V is the farthest member of the group. Yes, these are all the eccentricities, how closely it is related to the farthest member of the group. So we saw that the concept. Now C being the center can be considered as a leader of this group because mainly because of the closeness of the communication. You just need at max 3 links to communicate, at max 3 links to communicate the farthest member, so he can communicate easily. Based on that, it can be considered as a group. So such real things can be showcased via tree the situation, and for can solve if any some problems on this can be solved going forward. So it's just mimicking the real world entity into the tree. It's 2:20, so you're just left with one last concept. So I will take this concept in the next class. Okay, and I will stop here. Any questions? Oh. Sir, I understood radius, distance, diameter, but confused at center. Okay, sure. I will take that concept. I will revisit the concept of center in the next class. Radius, distance, diameter is fine. Okay, center is fine. So I'll meet you in the next class, probably tomorrow. afternoon slot, and we'll cover the rest of the topics under Unit 1. Okay? Yeah. Thank you, students.